I think we can get started. So today's lecture is about text generation. So we'll use this as a case study. So that from this case we'll see some principled algorithms that we'll be using in learning different models kind of. So what is text generation? So text generation is indeed a very broad research field. So the goal is to generate natural language from input data or machine representations. And there are many tasks relevant to natural language processing. So we can see like chatbot, right? Our input is an utterance, and output is a response, right? And for example, in machine translation, for example, input is an English sentence, right? And output is a Chinese sentence. And we have other tasks like summarization, like captioning and speech recognition. But all these tasks are about generating a sentence or like a paragraph, given a data or like a machine representation. So across all these tasks, there are two central goals we want to achieve in these tasks. First, we want to generate human-like grammatical and readable text. That is, we want to generate natural language, right? The language must be natural and realistic. And a second goal is that we want to generate text that contains desired information inferred from input. For example, in machine translation, right? We want given a source sentence, we want to generate a targeted sentence with the same meaning of the source sentence, right? And for like a data description, we want, say, given a table, right? We want to generate a report that describes this table. And there are other tasks like attribute control, right? Given a sentiment label, we want to generate a sentence like I like this restaurant, which has a positive sentiment. Or in like a conversational system, we want to control the conversation strategy and the topics, like. So basically, in this goal, we want to control the generation of the text so that it will contain the desired information we want. Yeah. So in this lecture, we will see different algorithms and methods that have been invented to achieve each of these two goals. First, as we know, a common model for text generation is the language model. So in language model, we calculate the probability of a sentence like this. So given a sentence, right, a sequence of tokens here, a language model basically decomposes the probability across this sequence of tokens. And for each step, we model this conditional distribution. Right? This is the distribution of this token, conditioning on the previous tokens. And there are many ways to parameterize this conditional distribution. For example, we can use an LSTM recurrent network. But this is the very basic language model, but it's the most commonly used in practice. But for practical tasks, we will always condition this output on some inputs, right? For example, in machine translation, right? X can be a source sentence and Y is the target sentence. Yeah. So in practice, we'll use this conditional language model. Right? So here, basically, we add some additional condition here in this distribution. Then with this model, how do we learn these model parameters? The most commonly used method is the maximum likelihood estimation. that is, at the training time, we'll maximize this data log likelihood, right? Given the ground truth data, y star, we maximize this log likelihood of this data. Here, we model this, we maximize this probability of generating this ground truth token yt, conditioning on the previous ground truth tokens. Right? This is how we train these models with by maximizing this log likelihood. Then after the training, right, how do we evaluate this model? Usually we use a task-specific metric. For example, in machine translation, we use a blue score to evaluate the quality of the output of the model. And for summarization, we use the Roche metric to evaluate the output. So yeah, basically these two metrics will evaluate the quality of a sample from a model against a ground truth. So we want to dive into the details of these two metrics, but basically we see that these two metrics are different from this data log likelihood. So with this common model and learning algorithms, here comes two issues of this method. The first issue is what we call the exposure bias. That means at the training time, as we know, right, we predict next token given the previous ground truth tokens, right? So at the training time, right, we feed in these ground truth tokens and predict the next token, right? This is what we did at the training time. But at the evaluation time, because we don't have these ground truth tokens at the test time, right? So what we do is we predict next token given the previous sequence that are generated by the model itself. Right? At the training time, we don't have this y star, right? So we have to use this token produced by the model itself. So we can see there is a discrepancy between training time and the evaluation time, right? Because at the training time, the model will never be exposed to its own mistakes, because it will always see these ground truth tokens. But at the evaluation time, the model made a mistake at this step. Then this mistake will be fed into the next steps, right? And affect all predictions in a sequel. So this is one problem of this this common method, maximum likelihood learning. And the second issue is that there is a mismatch between training and the evaluation criteria. Because at the training time, we maximize data log likelihood, but at the evaluation time, right, we use a blue score, right, for example, or for machine translation. These two metrics are different. So there is another discrepancy here between in terms of this criteria. These two issues are the most common issues in using maximum likelihood learning for training a sequence generation model. So how should we address these issues? Here are some possible solutions which have been proposed a couple of years ago. The first method, the most common solution to these issues is the reinforcement learning. So this topic will be covered in our next lectures, I guess. But here we'll just take a very quick look at this method. So in reinforcement learning, we maximize the expected reward under the model distribution. So we assume a reward function, for example, this can be the blue score. Right? So this reward function evaluates the quality of a model sample Y against the ground truth Y star. Right? And it will is a real valued function. So given a y and y star, it will return a kind of a real score, kind of, right? And we want to train this model to maximize this expectation. Right? Basically, we want this model to generate the samples that can maximize this reward function. Yeah. So what's the problem of this method? The problem is that because here y is a sequence, right? Y is a sequence of tokens. So this sequence space is actually very, very large. Assume like say we have a vocabulary size of 50,000. That means at each step, right? At each step we have 50,000 choices, right? And say we want to generate a sentence of like 50 tokens. Right? Then we have the sequence space is very large, right? And with this very large sequence space, the training will suffer from very high variance and poor exploration efficiency during at training time, right? This is the problem of reinforcement learning for sequence generation. And the more recent work proposed new algorithms for like a more practical training. The first is the reward augmented maximum likelihood method, REMO for short. So basically, in this method, we add reward-aware perturbation to the MLE data examples. So the intuition is that because for MLE, right, we have the exposure bias problem, right? The problem is that the model at the training time, the model only see the ground truth tokens, right? But how should we like close the gap between the training time and the evaluation time? The method here is that we want to add some noise to the ground truth data, so that the model will also see some like low quality kind of like mistakes or noise at the training time. So that this kind of like close the gap between training time and the test time. Right? And this noise is based on some reward function like a blue squirrel here. And the second method is softmax policy gradients. So in this method basically improves this basic reinforcement learning method. So here we can see to maximize in a standard setting, right? How do we maximize this expectation? We sample y from this distribution and evaluate these objectives, right? But especially at the initial training stage, this model is still like is still like not very good, right? So the samples might be of very low quality, and this kind of like makes this training suffers from like a high variance. So here in softmax policy gradients, we kind of reformulate these objectives so that the sampling will be based on both the model and the reward function, so that this sampling will be more efficient and kind of like produce better samples. And the third method is the data noising. The idea is basically the same with this REMO method. Here we add random noise to the data. The only difference is that here we add a noise which is based on a reward function, right? But in data noising we just add a random noise. Yeah, this is a sequence of different methods that have been proposed to address these two common issues in sequence generation. Yeah.
To reduce the bias between training and test conditions, why not just train on the labels generated by the model?
Yeah. So if at training time we just like fit the like a model prediction to predict the next token, then this is basically this method, right? So you can see here, we first generate the whole sequence, right? And the evaluate is quality, right? Right, so this kind of like the problem is that the sequence space is very large, so the training is very inefficient.
Like you just run the model once on the sequence using its own tokens that it generated, and you use the loss for it.
Yeah, so yeah, at the training time you can feed the list, right? Yeah. Predict token to list to generate next token, right? Yeah. That means you want to first generate the whole sequence, use by the model itself, right? So so this is the same problem in as in reinforcement learning, because you want the model to generate the whole sequence. And because this sequence space is very large, so very likely this model will generate a low quality example, kind of.
Just note on future courses, it definitely seems like if you get Y1 incorrect and then you're still predicting the real Y2, then you're learning something incorrect, which is like, if it was like fluffy cat, and you said some other word first, but you're still training it to say cat next, then you're like teaching the incorrect sentence. Like,
this is a problem of like of this MLE, because at the training time, you somehow like you use this as the input to predict next token, but if this is incorrect, then this model will be like a kind of we'll learn something that is not correct.
Question.
Yes.
On the camera capturing your pointer on the screen.
Yeah.
It is. Okay.
Yeah.
I asked all the people in fire lectures, so had a picture of the instructor, then
Yeah.
it had the verbatim, the direct aspect that you're saying this and that, if you want to follow it or something.
Yeah, cool.
Pretty cool. Right. Yeah.
Okay, so we have seen these different methods, right? These methods are all proposed with very different like perspectives, right? Say these two want like improves over MLE, and this method is basically based on this common like reinforcement learning, and it somehow like reformulate these objectives to like make this training more efficient, kind of. So then in a recent work, we kind of like establish unified perspectives of these diverse learning algorithms. We show that all these algorithms are indeed special instances of a particular framework called generalized entropy regularized policy optimization. So here we can see that different algorithms are indeed special instances, and the only difference is that is the choice of the reward function and the values of some hyperparameters. Say for MLE, we can reformulate this method to show that MLE is a special case of this framework with a reward function, which is a delta function, and with this configuration of these two hyperparameters. And the data noising is another method with relaxed reward function and the same like hyperparameter value. Yeah, and yeah, this is the framework. We kind of like connect all these different methods within a unified perspective. And with this unified perspective, we can inspire new and improved algorithms, kind of like to combine the best of all these different algorithms and overcome the difficulties like training difficulties or like the exposure bias. Yeah, let's take a look at this framework. So in general, let's consider a sequence generation model. Right? Given x, we want to generate y, right? And we consider a reward function, which evaluates the quality of a sample against the ground truth y star. Say this can be a reward function, right? It can be the blue score function. And again, we use the variational principle. We assume a variational distribution Q, and we have this objective. So here we kind of we can see we impose the supervision, the reward function on this variational distribution Q, right? And we encourage this scale divergence encourages the model P set to stay close to this variational distribution. Right? So these first two terms are kind of are indeed for standard variational principle objective kind of. Right. And we have seen this objective actually in our last lecture about combining domain knowledge with neural networks. Right? Yeah, and we additionally add an entropy regularizer Q, regularizer on Q. Right? This is the Shannon entropy, and we want to maximize this entropy kind of. Yeah, this is the objective of this framework. And this objective is a generalization or is very close to many popular RL algorithms like relative entropy policy search and like trust region policy optimization and all other stuff. We may see some of them in our next few lectures. But here we want to go into details of this different method. But this framework is basically this kind of is indeed pretty standard and very simple objective. And how should we optimize this objective? Again, we can use the EM style algorithm, right? Which we have seen in our last lecture. At each step, because this objective is convex with regard to this Q distribution, so we have a closed form solution for this Q. It's basically a kind of an energy-based model, and with this reward function and the model inside this exponential function. And for M step, again we just we find the relevant term with regard to theta, right? So we basically we want to minimize this scale divergence, right? So this is the M step. Let's see some intuitive interpretation of this algorithm. So here, say we assume alpha is very large, 10 to infinity. Then we can see that from this E step, right? Because alpha is very large, so we can ignore this reward function and ignore this beta. And then this distribution basically is like exponential and log p theta, right? Which is p theta. That means with a very large alpha, we get Q equal p, right? So yeah, and from this objective, we can see this the same conclusion, right? Because if alpha is very large, then we ignore these two terms and we minimize this scale divergence. That means the optimal solution is Q equal p, right? Yeah, and if we set beta to infinite, then we can see because beta is very large, right? So this is basically the temperature of the softmax function. So with a very large temperature, this Q distribution is a uniform distribution, right? And from this objective, we can see the same conclusion, because here, if our beta is very large, then we ignore these two terms. And we are basically like maximizing this entropy of this Q, right? So we get a uniform distribution. And yeah, these two are about the E step. Then for M step, we can interpret this as that we first get samples from this Q distribution. And then we maximize the log likelihood of these samples. Right? This is the intuition behind this M step. So here we are still like maximizing some log likelihood, but now we are using the samples from the Q rather than like ground truth data. Okay, so now we have established this general framework. We have this objective, and we have this EM algorithm to solve this problem. And then let's see how we can use this framework to recover these diverse algorithms we have seen, including the maximum likelihood learning and like RAMO and like softmax policy gradient. So this is the first instance. We want to recover the maximum likelihood learning. So with this algorithm, that's E step and M step, here we assume a specific form for this reward function, which is a kind of a delta function. This function says that given if the sample y equals the ground truth y star, then we return a reward 1. Otherwise, the reward is negative infinite. So this is basically a delta function, right? And we additionally set alpha to be a very small number close to 0, and the beta equals 1. Then we have this. We are plugging these things in. We plug these things into this E step and M step, and we see that for each step we get this function. We can see, like, say, now alpha is 0, right? So these two terms are canceled out, and beta equals 1. So this Q distribution is basically exponential R, right? And then because this R function is of this particular form, so that means like if y equals y star, then we get a kind of a non-zero reward, right? And otherwise, this is because this is negative infinite, so this is 0, right? So we get this distribution kind of. What does this mean? This is indeed the empirical data distribution, right? Because only when y equals y star, we get some like a probability mass, and for all other cases we don't have any like we don't assign any like a probability mass for other cases. So this is this Q distribution basically degrades to the empirical data distribution. And then at the M step, because at the M step we are sampling from this Q distribution and maximize this log likelihood, right, of these samples. And now that Q is the data distribution, then M step is basically maximizing this data log likelihood. Right. So with these configurations, our framework can like recover exactly this maximum likelihood learning. Yeah, this is the first instance. So what does this formulation mean? What new insight we can get from this formulation? So we can see that MLE is a policy optimization method with a delta function reward. So this delta function basically may provide any exploration beyond the training data. So we imagine that the whole sequence space is this box, right? And because of this reward function, the model is only exposed to these data points, right? To these observed data points, and any samples that beyond this training data will get a negative infinite reward. So that all other sequences will not contribute to the model training. So that means MLE is a very restricted method that restricts the model to only useless observed training data. But at the test time, right, this model is still there is no restriction for the model to generate a sequence. So the model can generate whatever sequence from this whole space, right? So we have this exposure bias problem. But this is the problem of maximum likelihood learning. But the advantage of this configuration is that we have a regular shape of exploration space. Right? So because here this Q distribution that just degenerated to the data distribution. So the implementation of this method is pretty simple. Right? We just sample from the empirical data distribution and maximize this log likelihood. So MLE is very easy to implement in practice, and which makes it very popular in practice. Okay, so let's move on to the second method, REMO. So how should we recover this REMO within this framework? You can see different from MLE. The only difference is actually this reward function. Here we set a reward function to be a common reward, such as the blue score between a sample and the ground truth. And we keep the two hyperparameters the same, alpha equals 0 and beta equals 1. And then we get this. Here now Q is no longer a data distribution. Instead, is a kind of exponentiated reward distribution. But this distribution is something like this. So usually, if this y equals this ground truth, then you'll get a very high reward. But this model also assigns some probability mass to other sequences surrounding this ground truth. So this is a kind of a more smooth reward compared to the delta reward in maximum likelihood. And again, in M step, we sample from this Q distribution and maximize this data log likelihood. Yeah, and basically this objective kind of recovers this original reward function REMO algorithm. Okay, so we can see that compared to MLE, right? REMO uses a task-dependent task reward. This reward is more smooth than the delta reward, and it permits a larger exploration space surrounding the training data. So here, given this training data, right, the model is allowed to explore a little bit surrounding this training data. And this somehow address the exposure bias problem to some extent. But we can see here, because alpha is set to 0, so you can see this term is ignored, right? Because alpha is very small. So this basically ignores the model distribution for exploration, right? Because all exploration is based on this reward function. Yeah, this is the method for REMO. But one disadvantage of REMO is that because here this reward function is more smooth, that means you can no longer just sample from the data distribution, right? So this makes the implementation of this method more difficult than MLE. Right? Basically, to generate a sample from this exponentiated distribution is pretty difficult. So there are some methods, there are some like works that propose some approximation method so that you can like approximately generate the samples from this distribution. Okay, then let's move on to a third method, the softmax policy gradient. We recover this method by with this configuration compared to REMO. Right? The only difference is the values of these hyperparameters. Here we set alpha to 1 and beta to 0. And again, we use the common reward function. Then what we get here is that we can see because alpha is 1, right? And we basically have these two terms in this exponential function, which is in this form, right? So, and then at the m step, we generate samples from this Q and maximize this likelihood. So this is the softmax policy gradient. And we see that this method uses both the model distribution and the reward for exploration. Right? This differs from the REMO, right? Because in REMO, we only use reward function to do exploration. But here, we use both for this exploration. And because the model distribution usually is very smooth, right? So that this exploration will explore the whole sequence space in theory. Right? So this method basically allows the largest exploration space. But the problem here is that because this space is very large, so this kind of like increase the learning difficulty. And then in practice, we may need like more tricks to like improve this exploration efficiency and make the learning really practical. Okay, so then fourth method, data noising. So as I said, data noising is basically the same with the REMO method, and the only difference is that here we use some like heuristics to like change this delta reward of MLE. Right? Here we use a locally relaxed variant. So this reward function says that if the sample differs from this ground truth with regard to only one position, then we'll return a reward 1. So this is kind of a relaxed variant of this delta function because here we allow a single token difference, right? And we keep this hyperparameter values the same with the MLE. And then with this reward function, we see that data noising is basically the same with REMO, but here in data noising we add a random noise, right, which is very easy to implement. And in REMO we use a reward-aware noise, which is more like difficult to implement. And the exploration space of the data noising is basically very similar to REMO because here we allow the model to explore a little bit surrounding this training data. Yeah, this is the data noising method. Okay, so we see that within this single framework, we can we show that every algorithm corresponds to a point in the hyperparameter space. Right? If we see the reward function and alpha beta as hyperparameters, then different algorithms are mapped into a single point in this hyperparameter space. And from left to right, we basically increase the exploration space, right, from MLE and to REMO and data noising, and to softmax policy gradient. But Yeah, this larger exploration space will, in theory, guarantee better, provides better test performance, right? Because this kind of like alleviates the exposure bias problem. But in practice, this also makes the training more difficult, right? Because the model has to explore a lot during training, which makes the convergence much more difficult. Yes, so with this new insight and this new understandings, right? Can we propose a new method that can address this problem and but still provide better performance? So one of these ideas is that we can do some interpolation among these algorithms. So the idea is that we start from this hyperparameter, starting from this point, and we gradually anneal these different hyperparameter values. Right? We gradually increase alpha from 0 to 1 and decrease beta from 1 to 0. And we can also use the interpolated function of this delta reward and the common reward. So with this interpolation, we kind of at the training time, we kind of gradually increase the training difficulty, right? And in the end, we'll ended up in this SPG hyperparameter setting. So that at the training time, the model will still see the whole exploration space, right? So this addresses the exposure bias problem, but the training will be easier because we start from the easiest setting and gradually increase the difficulty. So this kind of a progressive training can really help with this performance. So we did some experiments on machine translation and the text summarization. We can see this interpolation algorithm can improve over all these different baselines, these standalone algorithms. And for text summarization, we can also see this improvement. Yeah, this is the first part. To generate a human-like natural language, we basically want to address these two issues: this exposure bias and the criteria mismatch. And we propose a unified framework for sequence generation learning algorithms, including maximum likelihood learning, RAMO, softmax policy gradients, and the data noising, and also the standard policy gradient, which we didn't cover here. Yeah. Then let's move on to a second goal. We want to generate a text that contains desired information inferred from the inputs, in machine translation and data description, all these things. So this basically we want to do conditional generation, right? So how should we do this conditional generation? This really depends on the amount of training data we have, the amount of label data we have. For example, for machine translation, we have a large training data that consists of pairs of source and target sentences. And say we have tens of millions of training data. Right? With this large amount of training supervised data, we can simply use an end-to-end method. Right? Say use a sequence to sequence or use a transformer to train this model with supervised learning. And then for data description, we may have smaller data supervised data, but still the data is still very large, and we can still use a sequence to sequence or end-to-end learning. And but let's say for sentiment control, in this setting we may still have a large amount of label data. But for the second setting, say we want to modify a sentiment of a sentence, like from positive to negative, right? But keep all other properties of this sentence the same. Usually we don't have this data, right? We don't have these paired sentences that the source sentence is of positive sentiments, and the target sentence is of negative sentiments, and all other properties like the entities and other concepts in these two sentences, only in these two sentences are the same. Right? We don't have this kind of data. And further, like in conversational system, say we want to control the conversation strategy and the topics. Right? Again, in practice, we usually cannot collect such data like for direct supervised learning for conversational agents. So arguably, these two settings are more difficult because we don't have this end-to-end data. So in the next, let's discuss these two settings. Like we want to control the generation in these unsupervised settings. So we will see 3 applications in this setting. Let's see first. So these 3 are. So there are two levels of control. Like we want to control over at the sentence level and the conversation level. Let's first see the first instance. So in this task, we want to modify a given sentence to have desired attribute value, while keeping all other aspects unchanged. Say this attribute can be like sentiment, like tense and voice, and like gender. This is an example. We want to transfer sentiment from negative to positive. Right? Given this sentence, like it was super dry and had a weird taste, blah blah. We want to generate a sentence that is like it was super fresh and had a delicious taste. So we kind of like modify these 2 keywords from negative to positive, but keep all other aspects the same. Right? And the applications of this setting can include like personalized article writing, like conversation systems, and many other different applications. Yeah, let's see. Let's introduce some notations. So we have an original sentence x, right, and its attributes ax, and we want to generate a sentence y with target attribute ay. Right? So the task is that given x and ay, we want to generate a y, so that y has the desired attribute ay, and keeps all attribute independent properties of x. Right? And usually we only have pairs like consists of x and ax, but we don't have these sentence pairs, right? As I said. Yeah. So the solution here is that we first specify a model, which is a very simple like encoder-decoder model. Right? Given a sentence x, we first extract its latent features, and we concatenate this with the target attribute, and feed these 2 into a decoder to generate the target sentence. So this architecture is pretty standard, and we can use whatever architecture here, like attention, like like transformer, or these different architectures. And our focus is that how we can train this model without this direct supervision data. The key intuition here is that we decompose the task into competitive sub-objectives and use direct supervision for each of the sub-objectives. So actually, we already see these 2 objectives here, right? Say for the second objective, we want to keep all attribute independent properties. That means this y has to be very close to x, right? We want to keep most properties of x. So the simplest and the most straightforward objective is then just to autoencoding, right? Given x and ax, we want to generate the same sentence. So this sentence will keep every property of this input x. Right? Yeah, this is the direct solution we used to implement this objective. And second, for this objective, right, y has the desired attribute ay. Then we again use a very straightforward method. Given a generated y, right, we use a attribute classifier to recognize, to identify its attribute, and compare its attributes with this ground truth ay, right, with this input ay, right, and we can have a loss function here, right. So and we train this model to minimize this distance between the ground truth ay and the generated sentence and the generated attribute. Yeah, these are two first simple and straightforward objectives with loss functions for each of these two objectives respectively. And these two losses are competitive because basically this objective encourages the model to focus on this x, right, or focus on this z, right, and basically ignore this ay, right, because we simply want to reconstruct this x, right, with regard to reconstruct this x regarding a we want to ignore this ay, right. And but the second objective basically says that this decoder must focus on this ay, but ignore this z, right, or ignore x. Yeah, so these two objectives are kind of competitive, right? And they drive the model to different directions. But if we minimize these two together, we kind of join these two forces and push the model to the direction we want. Yeah, this is the intuition of this method, and we see that this simple method can produce pretty decent performance. We can achieve an attribute accuracy of about over 90%, and we evaluate the boost score against of the output sentence against the input sentence. This basically evaluates the similarity between this generated sentence and input sentence, and we get a pretty decent number of this boost score. But the problem of this method is that although we can generate accurate attributes and we can keep the property of the input sentence, but sometimes we can get these results. The original sentence is if I could give them a 0-star review, right? And the output is if I lied, give them a sweetheart star review. We can see that this model can indeed produce some positive sentiment right here, because sweetheart and light, these two words are positive words, right? But and also this sentence is pretty close to this original sentence, right? This model can keep all other irrelevant tokens the same, right? But the problem is that the language quality is pretty poor, right? This is not a correct sentence, right? And it's not natural. And we use a language model to evaluate this perplexity and get a pretty large perplexity, which means the language quality is not good. So how should we address this problem? Right. Again, this the solution is pretty straightforward, because here we want to improve this language quality, right? Or in other words, we want to like minimize, we want to get a low language model perplexity, right? Then the method is very straightforward. We just directly using language model as the supervision, and we train this model to minimize this language model perplexity. Right? We first generate a sample from this model and evaluate this, and we maximize this language model likelihood of this sample, which is the same as minimizing this perplexity. And with this method, with this additional objective, we get this accuracy like basically the same with this original one, and a blue score basically the same, but we can significantly lower this perplexity. And here's the result. So in this sentence, right, if I can give them a great star review, I would, right? So this is a correct sentence, and is a positive sentiment, right? And say in this example, right, from friendly to rude, right? This is a pretty decent sentiment transfer. Okay, so this is the first instance. For this task, the key idea for the solution is that we decompose the task into competitive sub-objectives, and for each of these objectives, we use direct supervision to achieve each of these sub-goals, and by jointly optimizing these objectives, we can get what we want. Yeah, and we can see this key idea can be applied to other tasks. So this is another task. Here we want to generate a sentence to describe a content in a given data record. Like here, this record is a box score of the NBA players, and we want to generate a sentence to describe this record. But language is rich with variation. Right? There are many different ways to express the same content. Right? We refer this as writing style. Like we have different word choice, different expressions and transitions and tones. Right? So in this task, we want to control the writing style. We want to use the writing style of a reference sentence to express this target record. So in this example, right, given this record and a reference sentence, which can be from a news article, right, or a previous news article. So we want to use this like expression, like led the way with blah blah points and assist, right? Well, this guy scored blah blah points. Right? We want to use this writing style to express this content. But again, we don't have direct training data, supervision data for this task. Okay, and the idea is that we still use the same the key ideas in our last task. We decompose the task into two objectives. Like first is this sentence must express this content precisely, right? And the second objective is that this output must have the same writing style with this reference sentence. Right? We optimize these two objectives jointly. And here are some results of this of our method. Given this content, right, X, and this reference sentence, which is about another player, our method can basically like generate a sentence that is what we want basically, right? Use the same like writing style. And but other methods like role-based method and other like adversarial learning methods, they can like produce some mistakes, because here like 5 rebounds we don't have list records in this. We don't have list number in list records, right? So these models can fail to like recognize this difference between the reference sentence and the record. Right? But our model can see like you can see like we can generate the we can express this content very precisely, you know. Yeah, and here's some here are more results. We evaluate these two objectives, kind of like how well this model can like keep the writing style of the reference sentence, and how precise this model can express this content. Right? And we can see this our method can get like most balanced and kind of like best performance for these two objectives. You know. Okay, so let's move on to the third instance. So now we want to control generation at the conversation level. Again, we'll still use this key idea for this task. So in this project, we want to use conversational agents. And there are two, as we know, in conversation research, there are two paradigms of dialogue systems. The first is task-oriented dialogue. Right? So in this dialogue system, we want to address a specific task, like booking a flight. And usually this dialogue is closed domain. All the conversation with dialogue agents must be about like booking a flight. And the second category of conversational agents is we call open domain chit chat. This agent is usually used to improve user engagement, and the conversation is random and hard to control. So in this task, we want to do something in between. You know, we want to target guided conversation. This conversation is an open domain conversation, and we want to control the conversation strategy so that the conversation will reach a desired topic in the end of this conversation. And this type of conversation can be useful in practice, like recommender systems, right? Like starting from whatever topic, the agent will talk to the user and will guide the topic to a specific an entity or like a specific product, so that this agent can like start recommending this product to the user. Let's see an example here. Say our target is ebooks, and starting from whatever topic, like a generic greeting, like, hi, how are you? How are you doing? Right? And not so good. I'm really tired. I'm sorry to hear. I have a lot of work to do. What kind was it? I'm writing a chatbot program. Right? And the agent says, I read about coding from a book. And then it translates this topic to like, I prefer ebooks over blah, blah, right? And in the end, this agent can achieve this target. And we can see there is a very clear backbone of this topic throughout this conversation. First, like the keyword is tired, right? And sorry, and it's about work. And then program. And at this point, the agent can capture this chance, right? It kind of like direct this topic to coding and further to book, right? Book is certainly like closer to ebooks, right? Closer to this target. And then in the end, the agent translates the topic from books to ebooks. Yeah, so in this task, we want to achieve two goals. First is that starting from any topic, we want to reach a desired topic in the end of this conversation. This is a target-guided objective. And second objective is that, of course, we want this conversation to be natural, right? This transition must be very smooth. Right? This fulfills this open domain requirement. And the challenge here is that, again, we don't have supervision data for this task. And our solution is, again, we use this key idea. We decompose this task into different sub-goals, and we use partial supervision for each of them. In particular, for natural conversation, we use the rich conversation data to learn this smooth transition in a single turn. Right? And to reach the desired target, we use a rule-based method. We kind of constrain the agent to choose the next topic, so that in the end, this topic the agent can reach the target topic. Kind of. Let's see this framework. So, given an utterance, right, from a human, like this utterance, the agent first extracts the keywords from this utterance or the topic of this utterance, which is program. Right, and then the agent pick the next topic, like coding and book, and with this topic, the agent generates a sentence, generates a response. Here we use a retrieval-based method. We use these keywords and this history to retrieve a sentence, retrieve a response from a database, right? Like this. But of course, we can use like generation-based, right? Conditioning on these keywords and the history, we can generate a sentence. Like we can generate a response. Well, the key part of this framework is that how to learn this topic transition. Right? We use two strategies here. First, to make sure this transition is smooth, we require the agent to translate to keywords that are close in the word embedding space. All right, close to this original keywords. So let's make sure this transition is smooth, right? Because the semantics of this next keywords is similar to the semantics of the original keywords. And the second, we require this next 8 keywords must get closer to the target keywords. So that throughout this conversation, the topic will move towards this target, right? So this kind of fulfill this target or target guided goal. And we combine these two constraints together, and we can tune these relative weights of 1 and 2 to control the aggressiveness of these agents. Okay, so we can see basically we decompose the whole task into these two objectives, and we use very simple constraints to implement these two objectives. With this framework, we get some pretty interesting and high quality examples, given a target the dance, right? And starting from this random topic, right? We can see here you can see some key transitions. Here, I also like basketball, right? You like rap music, right? So the agent can capture these keywords and translate this topic from sports to music, right? Because music is closer to dance, right? than sports. Right, and then in the end, I know nothing about singing, right? And the agent said, "Oh, I think I can dance." Right? So this translate is from I know nothing, and I think I can, blah blah blah. So So you can see like this agent can somehow like balance between this smooth transition and reaching this end goal. But of course, this method is still pretty simple, and it can produce some failure cases. Say here with targeted lesson, right? You can see like human said, "What's your new job?" Agent said, "That sounds exciting." So you can see like this transition is not very smooth. And I read comics. I don't have TV, right? So this is basically not a correct, not a natural conversation. Right? Okay, so this is 3 instances we discussed in the setting of like unsupervised controlled generation of text. And the key idea is that we decompose the task into sub-objectives, and these objectives are competitive with each other. So that we can use like a direct supervision to optimize each of these objectives, and by combining this, by gently optimizing these objectives, we can prevent the model from like collapsing to a trivial solution. Okay, so we have seen these different algorithms and applications for these 2 goals. Basically, to summarize, for text generation, we want to do these 2 goals. Like we want to generate natural language, and we want to control this information in the generated text. Right? And here we see some like a unified framework to address the key problems in generating natural language. And here we kind of like use a principled method, like decompose a task into sub-objectives, and do joint training kind of, so that we can do like unsupervised learning for these complex but very interesting real applications. Yeah, so this is pretty much of this lecture. Yes, there's time limit. If you have any questions, we can like discuss offline.